My project to make a homemade oscilloscope with nothing more than an Arduino, $20 to $30 and free computer software is now complete. Now is the time I would like to show off all of the features as well as how the code works. So this is going to be the first code review that I do. This channel is not just electronics, it's only electronics themed. Now I understand if my usual viewers aren't that interested in programming, but rest assured it will be simply put like everything else, so even if you don't understand programming, if you're interested, feel free to watch. You might not be able to read the code or write it yourself, but you'll still understand how the pieces work and how they're put together. The same way that you can understand how a transistor works without understanding quantum mechanics. So I hope you'll stick around, but if not, I'll see you next time. So this is the Arduino program. There's code that runs on the Arduino, and then most of the code runs on my computer. In this case, it runs on my laptop. It could run on anything else you have. The idea is to keep the code on the Arduino as simple as possible, because the Arduino is the more low-powered device. The purpose of using the Arduino is that it is inexpensive, $20 to $30 like I said, the price of 2 nights at the restaurant, or 1 if you go to a really good restaurant, and it's so simple and easy. It has a built-in software interface, IDE, a built-in analog to digital converter with all of the bells and whistles. It's just plug and play. And the Arduino, of course, is reusable. You just put different code on it to do whatever you want at any time, and then anytime you need an oscilloscope, you just run this and hit upload. So while it's uploading, the setup program runs one time when it first boots up, when the Arduino starts, or you press the reset button. The loop just runs over and over and over and over and over and over and over forever. Serial begin 500,000 bauds, so that's 500,000 bits per second. That's actual bits, data bits. See, there are 8 data bits per byte. This uses the 8N1 default settings. So it's sending 8 data bits, but it uses 2 extra bits for every one of those bytes as overhead to make sure that the connection is proceeding smoothly. So if you divide this number by 10, you get the data bytes per second. So this can send a maximum of 50,000 actual bytes per second. And since each sample we're reading is 2 bytes, that's 25,000 per second. Now, it's actually going to send about 8,000 per second. The reason for having this higher is even though we cannot saturate the connection, even though we can't send data as fast as possible, those data will still arrive faster. If we send 1 byte, it will arrive in less time, and then we'll go back to idling. And this number is what I have arrived at with testing. It's a nice round number for my setup, my electromagnetic environment, my laptop, my Arduino, my code in general, that gives me no transmission errors that I can see. If there is an error, it's every once in a while, and it just goes away immediately. Because this is not like transferring a file. If you transfer a file and you get a bad byte, that byte stays bad and it's corrupted the file. But this is a display, and so that bad byte just goes away. The data are disposable, I guess you could say. So if it gives 1 error an hour, I'm not going to worry about it. So it starts up the serial connection, boom. And then over and over and over, analog read, it'll take pin number 0, and it will read that analog value as a number from 0 to 1023, so a 10-bit unsigned integer. And then I write 8 of those bits, well, in this case, 2 plus 6 padding bits. So, because 2 bytes is 16 bits, we use 10, so I write 6 bits that are always going to be 0, and then 2 of the data bits, and then the last 8. This is called big endian order. But in any case, that's it. That is the entire Arduino program. Nice and easy. It just reads and writes and reads and writes and reads and writes at the maximum speed. And this is my oscilloscope. I have made it in the Unity engine in the C# language. I will show you how the program works first, and then I will show you the code. So if all you want to see is the features, you can bow out after that. I do hope you stick around, but we'll see. So COM3 is just whatever Windows decides to call the port. In your Arduino software, when you're selecting which board, which port you are, it'll just list everything that's connected, and you can see COM3 right there. So you can just use the Arduino software to find out what it's called. The baud rate is going to be 500,000. 8N1 is the default, so that's 10. 1 stop bit, 1 start bit, which is implied. Connect. So right now, the Arduino is reading its analog signal and there is nothing plugged in. This is a floating input. So it's wiggling around as I move my hand, as I move the USB cable. It's just reading whatever induction happens to be there. So as you can see, it's steadily reading about, if this goes from 0 to 5 volts, then this is around, I'd say, 2. Of course, there's no actual main current there. There's only induced current, but it's enough to get a reading. Now, if I put a wire in from the analog 0 port, now I've got a long wire connected directly into that port, and I'm reading waves that happen to be nearby. And if I touch the wire, funky things happen, but this is not useful. I have now plugged the wire into digital pin 3, and of course, more garbage. So I'm going to disconnect, and I'm going to add something. Oh, and I should show you. Let me connect again. Over here on the left, if there were errors, it would say there are errors. There are no errors. If I apply these settings, at some point it'll say an error. That's because I hit apply halfway through reading a sample. All right, see if I clear it out, there's no errors. That just means I reset it when it was in the middle of a sample. So it detected the other byte and was like, wait, that's not a complete sample. 8300 hertz, relatively stable. It's reading as fast as it can. So that's the actual reading rate. Now, disconnect. I'm going to go in here and add something. Analog write 364 and upload. I had to disconnect the oscilloscope because the oscilloscope was using the USB port, and obviously uploading code to the Arduino uses the USB port. So there we go. Now, connect again, and we get no garbage anymore. You might be able to see at the top. So let me show you the first feature. Still getting 8300 no errors. So if I change the display height, so basically the samples go from 0 at the bottom to 1023 at the top. And I have a display height, which is how many pixels I'm compressing that to. So right now, my display is 1080 high, but display height is 960. If I change this to 1080, then this is exactly as tall as my screen is. If I cut it in half, 540, you'll notice you might be able to see the blue dots now. They're now 2 pixels big. So display height just creates an image that high. And whenever it draws samples, it fits those pixels and stretches them if necessary to fit in that area. So if I do 100, can you see they're getting taller? If I do 50? So at this point, every pixel, there are 50 pixels. So 1080 tall is the actual display, but there's only 50 rendering. If I do 2, see, there's only 2 pixels in this image, and it's being stretched to fit vertically. So any sample from 0 to 511 is going to be this pixel. Anything from 512 to 1023 is going to be this pixel. That's what display height is. So let's do 16. So the point of this is just to make signals easier to see. You can have more precision, or you can have them be bigger. So right now, that analog write command is PWM. This is a PWM signal. 64 means 25% of the time. So 25% of the time, it's high. 75% of the time, it's low. You can see that. So now, well, first of all, let me go over this. Sample bytes, there are 2 bytes per sample, because we're sending it there, because 8 bits in a byte can't hold 10 bits. The value is 10 bits big. This is where I say it's actually 10 bits, so that tells my program to expect 6 bits that are blank. And max sample is just the maximum value. So the highest this value can ever be is 1023, the minimum is 0. So that's not going to change if you're using the same Arduino. Now display width is the same thing. So if I do 2, the thing's only 2 pixels wide, and you can see them flashing as they change value. So every 2 samples, right? Whereas now, 512 samples are being stretched to fit the screen, and then it's overwriting every 512 samples. We're getting 8,300 per second, so this is being overwritten many times per second. Now, here's a trick. You may have seen this before. So right now, it's going to the left, so let's try decreasing this. Now it's going to the left more slowly. Let's decrease it again. And a real oscilloscope would have knobs for this, and it would be more precise. See, it's slowing down, and eventually it'll switch direction. 508. Oh, see, it switched direction. If you look very, very, very carefully, you can see it's actually going to the right super slowly. So what does this mean? Well, every 508 samples is being drawn across the width of the screen, and then the next 508, and the next 508. And so, because there's almost no motion, that means, however many of these waves there are, this many of them fit almost perfectly in 508 wide. So it's almost drawing the same wave over top of itself. So that's a technique you can use to visualize a waveform. You can change your display width to get it drawing over itself, so it'll be very little wiggliness or no wiggliness, and you can kind of visualize. Now, also, I added a pause feature, so you can straight up just pause. So, if I go over here and let's say I do 200. So that's pretty wild, but if I pause, now we can just see it that way. But that doesn't tell you about how big it is, you'd have to calculate. So both ways work, unpause. Now, one other thing is pause at next change. So if I do that, it immediately pauses because the samples are changing wildly. Let me go over here and disconnect again, and I'm going to analog write 0. So this is going to just turn it off. It'll be 0 volts essentially. Connect. It reuses the same settings as long as you don't close the program. So now you can see it's all at 0. Now, I'm going to say pause at next change, and it's not pausing. See, it's not paused. I'm going to now unplug the wire and let it read whatever crap there is in the air. And immediately, you can see it pauses. So it reads a full waveform of whatever's going on and stops. Let me plug it back in and unpause, and it starts reading again. Now, let's increase this to 1000 and display height to 400. Let's do 200 so we can see it better. So you can see a blue bar at the bottom. Pause at next change, and then I'll unplug the wire. There we go. So then you can see what happened was it was right here. This spot right here was when the first sample was not low, because they were all low, and then all of a sudden one of them was not low, so it paused. And then it starts reading and reading and reading whatever crap is in the air until it gets back and stops. So the pause function, if we turn it off and on again, see, you can see wherever the break happens to be there. That time the break was there. Now it's over here. It's just wherever I press the button. That is how you get to see a specific event. Like if you're not trying to watch a consistent waveform, if you're trying to say, I want to see what happens when this button is pressed, then you have, it's always 0 or max or whatever. And then as soon as you press the button, there's a change so you can see what's going on at that moment. Let's go back to 16 and let's do 508, I believe it was, and then disconnect, and I'll get my PWM signal back to 64. So there it is. And yes, 508, so that's about right. Now, the final thing I want to show you is group size and group mode. So this PWM signal is about 25%. So if you powered an LED with it, it would be about 25% bright. If you read it with the DC voltage setting of a multimeter, because this is varying, this is, AC essentially, but if you read it with the DC setting, you would read about 1.25 volts, because this is 5 up here, so 2.5, 1.25, because it averages over a period. So let's say we want to do that. Well, let's pick a group size of 16, and then let's just say maximum. So what happens now is every 16 samples is grouped together as one effective sample. So you group size 1, every single individual sample is being shown. But if I increase it to say 16, every 16 samples is going to be added together or I should say combined, not added. In this case, it's taking the maximum value of any of those samples. So what this tells us is every 16 samples, and we can see how often that is by looking at the frequency as well, because this is samples per second right here. So if you have 16 samples, this many samples per second, you can get seconds. So at least one sample out of every 16 is high. What if we do minimum? At least one sample out of every 16 is low. There we go. Now, something more useful. Those are useful in certain situations, if you're trying to cut out noise, but how about mean? Now looky there. That is right about, if you kind of look at it, it's in the lower quarter, because we said it should be about 25%, right? Well, that's in the ballpark. Let's increase the group size. Looks better, doesn't it? Let's do 100. Almost all of them. Right about there. Let's do 200. Nearly perfect. So what's happening here, and even if we increase display height, it'll look even better. See, because now we're getting more resolution, we can see it's a little fuzzy. But the point is, it's all about there. This is how PWM generates an effective voltage. Because it's turning it on and off. But if you're measuring over a larger span of time, over bigger chunks, it ends up being effectively that voltage. And that does work electrically. In the strictest sense, you are turning something electrically on and off and on and off and on and off. But it behaves on the grand scale as if you were simply giving it a lower voltage, with the trick that you could make an effective operation of a diode below its forward voltage drop, because you're actually not operating it below its forward voltage, but it's behaving as if you were, on the grand scale, on the human time scale. Electrons have a much shorter time scale, and that's why it's fuzzy. But for us, we have a much greater time scale. See, 400 samples? This is still 8,000 per second. So even if I do 830, that's still 10 per second. We can certainly perceive 10 per second, but it's nearly perfect. Go back to 16. So that's the mean. What about the median? The median is all low. So out of each 16 samples, the median is always low. Let's make this easier to see. Now, what is the median? If you're not familiar with statistics, the mean is the average. The min and max are obvious. The median is where you take all of the values and you sort them from low to high, and you just take the middle one. You're not averaging the values, you're taking the middle one. So if you had 10, 20, and 30, then if you add them together and divide by 3, you get 20. And if you sort them, the middle number is 20. Now, if you do this, your mean is going to be a lot higher than 30, but your median is 30. You just take the middle value. Now, the reason you do this is to remove something called outliers. Imagine you have this. So this is your list. If you take the average, you're going to get a very high number because of this one single number. Even though you can obviously see, almost all of these are about with each other. So if you took this one out, you'd get a good mean. But this one screws up the mean, but if you take the median, you'll just get a 3. That's what the mean and median are. So right now, it's operating 25% of the time. So let's say it looks like this. 25% of these numbers are 1, but the median is 0. That's why we get low. Let me change this to 192. That is 75%. And I have to disconnect the oscilloscope to upload the new program. So if we connect, we see there median, we're still on median, is now high because our list looks like this. So now it's on 75% of the time. So the mean would be 75%, 0.75, but the median is going to be in here, so you just take one on either side, and there you go. It's 1. So if you have a noisy signal, but the signal itself is stable, of course, if the group size is 1, none of these things have an effect. So you can see that this signal is stable. But what if there was a bunch of noise? You can take the mean, or you can take the median, and that's 2 different ways of trying to see through the noise without actually filtering the noise out. And that's the oscilloscope. That's it. So now let's look at the code. So as you can see, I have created this in the Unity engine. This is free for anyone who's not making $100,000 a year, which I most assuredly am not. So I'm not going to go through a Unity tutorial or a C# tutorial. You'll be able to follow along even if you don't understand what's actually going on, but I'll give you the basics. So over here, I just have an empty object that has my different parts in it, and this is how I set my variables. This is how I link parts of the program to parts of the interface. This is the camera that's shown. All right, you can see I'm just using it that way, just a regular orthographic camera. So here's the actual UI. So we have 3 parts. The setup interface, which is just a button and a bunch of text entry fields. See, input field, that's all it is. Configuration is the same. It's some text entry fields, a button, a couple buttons, a couple text displays, and a couple checkboxes. It's just UI stuff. No code does anything here. I just created what was pretty. And the final piece is the sample display. This is just a container for a texture, and it's blue. This sets what color it draws as. So in the program, it creates the texture at runtime. It creates the texture and puts it in here, and that determines whether or not it shows a pixel of this color or nothing. And it shows through because the camera, you can see clear, it clears to white. So the background is always white. The foreground is always blue, and the texture says whether or not to draw a piece of the foreground or let the background through. It's called using the alpha value. That's all it is. Now for the code. So first we have the serial port manager. So this is a little thing I do. These are called singletons. If I'm only going to have one serial port manager in the program, see, it's up here, serial port manager, there it is. See, it's just one of them in the program. It's not creating multiples, it's just one, it's a singleton. So I create a static of it, and on awake, this is how Unity does constructors. It just sets that instance. So over here, it just creates a list to hold the bytes. So I connect using, see, we set the baud rate, data bit, parity bit. It just reads from these strings, from these entry fields. Well, not these, but you know what I mean. It reads the strings and converts them into parameters of this function, and it opens it up. On disconnect, it closes, and then it just calls this function. The main oscilloscope calls this function repeatedly, read bytes. So it clears the list. Every time there's a byte to read, it adds it to the list. When it runs out of bytes, it just sends them up. It does not process the bytes. It just reads them and sends them up. It is good to keep parts of your program separate. Even though you could write this as one big function, it is a whole lot easier to maintain this way. So then we go over here. Here's another way to see all my stuff. So once the serial port manager gets the bytes, it goes to the byte processor. So the byte processor maintains all of this. So it initializes, it creates a list of samples that it's going to get. Now configure, this is this screen. Configure it with sample bytes and all this stuff. So remember how I said it's 2 bytes, but it's only 10 bits, so the top 6 bits are going to be 0 every time? This is how it detects errors. It creates a mask. So for the lead byte, the first byte, it masks out and it checks to make sure those 6 bits are null. If those 6 bits are null, it assumes it's a valid sample and continues on. Otherwise, it skips the byte and it marks as an error. So this is obviously not perfect error detection, but it's plenty for my purposes. This is more than enough for a simple oscilloscope. You would not want to write a life support unit or part of the space shuttle using code like this, but something like this perfectly fine. So the actual program is this. So the input is the bytes from the serial port. It goes through. If this is the first byte, it checks to see that those bits are indeed 0. If they're not, it marks it as an error. If they're fine, it says, okay, now the rest of the bytes we're not going to check because there's no null bits. They're all data bits. So it just accumulates and then it sends out samples. It does not process the samples. All this is doing is reading bytes, checking them for errors, and sending samples out that are the bytes stuck together with glue. Again, encapsulate. It's easier that way. So then we have gone from the serial port to bytes. We've gone from bytes to samples. Now we're processing the samples. Here are the group modes. This is just how it keeps track internally. When you configure it, it takes the string, and you should use a drop-down box instead of a string. I just did it this way because it was easier for me. And it sets the mode. And then here are the 4 functions. Minimum goes through all the samples and finds the smallest. Maximum goes through all the samples, finds the biggest. Mean just adds all the samples together and then divides by how many samples. And the median simply sorts the list and takes the one in the middle. And then process samples, the input is the samples from byte processor, just the list of samples, however many we have received in full. So for each one, it adds them to a list anytime that list gets to be group size. So if group size is 1, it's doing every sample separately. If group size is 16, it maintains a list of 16 values. When that list fills up, it calls this function and then clears it out and starts accumulating another 16. And of course, if the group size is 1, the list fills every single time. This is obviously inefficient, but it's no big deal. I'm trying to process some 8,000 values per second. This laptop is a dual core 3 gigahertz. That's billions per second. It can handle it. So in order to make easier code, I'm wasteful. There's nothing wrong with that. I don't work for Keysight Labs. So anyway, that's the entire sample processor. The output is processed samples. They're grouped up. They're minimum, maximum, whatever they are. They've been run through these functions. And so these are ready for display. So then they get to send to the display manager. So this is what creates the texture. So when you configure, that's when you hit apply. It figures out the width and height. It creates the texture, makes sure that it's only an alpha texture, no filtering. It just draws it. Because if you don't set the filter mode to point, it gets fuzzy. You can still see it, but I don't like it fuzzy. And then just initializes everything. It sets the texture, clears it. Everything's nice and empty, and it's not paused. So then the input is the processed samples, ready for display. So this reads the checkboxes. It does not act on the checkboxes immediately. It maintains an internal variable paused. It's a lot easier this way. It's, again, more wasteful, but it's easier to code. So this handles if you check the box to pause it and it wasn't paused before, it pauses it. Otherwise, if it's not checked and you are paused, unpause. Then it processes the samples. If you're paused and it's already filled up with samples, it just ignores them and continues on. Otherwise, it accumulates however many samples to fill the window before not drawing anymore. So this one, it clears, so it's like a sweeping from left to right, and then it wraps around. Just like the way the old oscilloscope worked, which was with a cathode ray tube and green phosphors. It would just wrap around. So it clears the current sample, calculates the new sample. This is where it detects if there's a change. If we are trying to pause when there's a change, and there was a change, pause. Otherwise, it doesn't do anything. And then it adds the sample, and then at the end, after it's processed all of the samples that are available right now, it updates the texture in memory. Status display is just the frequency and the error count. So I just give it the samples, and it sets those values. Adds one to the error count, and it processes how many samples and figures out about how many per second that has been. So that one's real simple. Now, the actual oscilloscope. So at the beginning, we just clear everything, initialize everything, and set it to its default state. When the connect button is pressed, it sends a message to the serial port manager. Same for the disconnect button. This just forwards messages. See, this one does all the configures, the apply button. And in addition, you can see on connect, it also does apply. So that sets the settings when you first connect. Handle configuration toggle. This is when I press spacebar. spacebar. All that's doing is turning this screen on and off with the spacebar. So this just loops. So if the display container is not active, display container is the sample display, remember? The blue? If that's not active, then there's nothing to do. We're not displaying samples. We're not reading or anything. We're just on the setup screen. So if we're not on the setup screen, if we're actually doing something, check for space, toggle that if I've pressed spacebar. Otherwise, read from the serial port. If we read something, then we process the samples, keep track of how many errors there were in processing. If this screen is displayed, then display how many errors. If we're not displaying the configuration, there's no use in updating this, so we just don't. But if it's up, we'll update it. And then if anything actually came in, if any full samples did, we might have gotten a byte, but not a full sample. So if a full sample came in, then the status display manager, update the frequency, that just counts the samples, and every second it calculates hertz from that. And then you process the samples, and you display them. That's it. That's it. Completely free software and an Arduino. And that is more than long enough for a video that most people aren't going to watch. But for those of you who did, thank you. And I hope you got something out of it. If nothing else, it teaches you ingenuity. I spent time doing this. I could have instead simply bought an oscilloscope. But that's also time, because that's working time. I have to work to make the money. And that's a lot of money, which means a lot of working time. Now, I would have gotten a better product than the one I made, but this one does what I need it to do on a basic level. It's not a good oscilloscope, but it is an oscilloscope. And it cost me nothing because I got the Arduino anyway. I'm doing electronics with it. So technically, I got a free crappy oscilloscope. And of course, I learned lots of things in the process. Someday I'll get a real oscilloscope and show it off, but today is not that day. So until the next day, be seeing you.